Welcome students. Let's see Bspline in this session. We have already seen interpolation techniques to generate a smooth curve. It must passes through all sample points. It means the sum of blending functions must be 1. For every sample point for integer values of given figure. We may get blending function as 1, but for fractional values we may not be able to pass the curve to the sample point. The questions can be asked like explain the techniques of smoothing of curve using Bspline. So this example we already completed in last session. Now let's see the answer for explaining the technique of smoothing of curve using Bspline. Suppose that there are 5 sample points as shown in figure. We may fix up a curve from the sample points as shown in figure. Suppose there are 5 sample points as shown in figure A. We may fix up a curve from the sample points as shown in figure B. If the blending function is 1 for all values of A. These are the 5 points. First point, second point, third, fourth and fifth. And if we are having the blending function value for all these 5 points of figure A as 1, we can get a curve which look like this. Due to blending point function value 1, this curve has strictly need to pass through all these 5 points. First point, second point, third point, fourth point and fifth point. We will come to know that each section of the curve is connected to the other section of curve at sample point. If you considered one section between these 2 points, that is correct. Second section between these 2 points, that is also connected. Third section is also connected. Fourth section is also connected. And the fifth section is also connected to the sample points. But the slope of 2 sections may be different. So we are getting corners in the curve. That's why the slope of this section is different, slope of this section is different. So we may get corners at the sample points. It means the curve which we are getting is not smooth. In order to go near to the smoothness of the curve, we will pull the curve in such a way that the curve will pass through one sample point only. It means the blending function will be 1 for only one sample point. By using this technique, we may eliminate the sharp corners. Just check out this sample figure C. Here this first sample point, we are having blending function as 1. Second, we are having some other function, blending function value that is ranging between 0 to 1, but not 1. For this also not 1, not 1, not 1. But this will not give us natural appearance of the curve. So here we will not try to force the curve to pass through the sample points, but rather gently pull it into the neighborhood of the sample point. So by doing this, we will get a smooth curve which is not passing through any of the sample points, but still maintains the original shape of the curve, which is shown in figure D. So these techniques are there for smoothing of curve using B-spline. We require to set blending function at each sample point. First sample point, second sample point, third sample point, fourth sample point, fifth sample point. The values of blending function of all the sample points must be other than 1. Then only we can get a smooth B-spline curve. A set of blending function which takes this approach is called B-splines. Basically, spline means a strip which we have to move around the sample points. Generally, the B-spline blending functions were designed to eliminate the sharp corners in the curve, and the curve does not usually pass through the sample points. But if we need sharp corners, we can produce it by using many identical sample points, which is shown here with the help of these figures. First figure shows the curve using one sample point. This one is that sample point. Second figure shows the curve using two identical sample points. Here we are using the 2 points which are identical, and that's why the curve is moving towards more to the sample point. It means we are calling the blending function for the same sample point twice. And third figure shows if 3 identical sample points are used, the curve will be forced to pass through the sample point. We can have some properties of B-spline curve as the maximum order of the curve is equal to the number of vertices of defining polygon. The degree of B-spline polynomial is independent of the number of vertices of defining polygon. B-spline allows local control over the curved surface because each vertex affects the shape of a curve only over a range of parameter values where its associated basic function is non-zero. The curve exhibits the variation diminishing property. Thus, the curve does not oscillate about any straight line more often than its defining polygon. The curve generally follows the shape of defining polygon. Any affine transformation can be applied to the curve by applying it to the vertices of defining polygon. The curve line within the convex of its defining polygon. The curve line within the convexal of its defining polygon. These are some properties of this spline curve. Let's move towards the next point, that is Bezier curve. What is Bezier curve, or how we can produce the Bezier curve? Bezier curve is a different way of specifying a curve. Rather, same shapes can be represented by B-spline and Bezier curves. The cubic Bezier curve require 4 sample points. These points completely specify the curve. This figure shows sample Bezier curve. The curve begins at the first sample point. Here the first sample point is A, and ends at the fourth sample point, which is here the point B. This which is and ends at the sample fourth point, that is D. If we need another Bezier curve, then we need another 4 sample points. But if we need 2 Bezier curves connected to each other, then with 6 sample points we can achieve it. For this, the third and fourth point of first curve should be made same as first and second point of second curve. There are few set of equations of Bezier curve with which you can generate Bezier curve. The equation for the Bezier curve are as follows. X is equal to x4 a cube plus 3x3 a square 1 minus a plus 3x square a 1 minus a whole bracket square plus x1 1 minus a whole bracket cube. These x4, x3, x2, x1 are the x values of 4 sample points, and a is our blending function, which is ranging between 0 to 1. Same for y. Y is equal to y4 a cube plus 3y3 a square 1 minus a plus 3y2 a 1 minus a whole bracket square plus y1 into 1 minus a whole bracket cube. If we have z point, then we have z value calculated as z is equal to z4 a cube plus 3z3 a square 1 minus a plus 3z square a 1 minus a whole bracket square plus z1 1 minus a cube. Next, we will see Bezier cogeneration using midpoint subdivision. The question was asked many times on this. Explain Bezier cogeneration using midpoint subdivision algorithm. Here, as the value of A moves from 0 to 1, the curve travels from the first to fourth sample point. This is our first sample point and this is our fourth sample point. But we can construct a Bezier curve without referencing the equations of Bezier curve, which we saw earlier. It is constructed by simply taking midpoints as shown here in this figure. The points A, B, C, D are the original Bezier curve control points. Here we are having 3 lines AB, BC and CD. Then we have to find the midpoints of these lines as P, midpoint for BC as Q and midpoint for CD as R respectively. After that we have to join PQ, QR, then again find the midpoint of this newly generated line as S. For PQ we are having midpoint S, U as For QR, you are having midpoint U. Then form a line which is going to connect S and U and find midpoint of this line as T. Now point T will be on Bezier curve. This point T divides the curve into two sections. One is APS and T and second will be DRUT. DRUT. Thus, by taking midpoints, we can find a point on the curve and also split the curve into two sections. We can continue to split the curve into smaller sections until we have sections so short that they cannot be replaced by straight lines, or till the size of section is not greater than the size of pixel. We may get some numerical problems or examples also on these curves, like obtain the curve parameters for drawing a smooth Bezier curve for, let's say, points A 00, B 1040, C 7030, D 6020. We can calculate by using the equations of Bezier curve for x and y also, or we can have simply calculation of midpoints for each line and then we can calculate it. Then we are having next point, that is cubic Bezier curve. Cubic curves are commonly used in graphics because curves of lower order commonly have too little flexibility, while curves of higher order are usually considered unnecessarily complex and make it easy to introduce under undesired wiggles. To join multiple curves into one curve smoothly, we need to specify the position and their tangent vectors of both ends, that is the continuity requirements. Let's see example given here in this figure. 4 points P0, P1, P2 and P3 in the plane or in three-dimensional space define a cubic Bezier curve. The curve starts at P0 going toward P1 and arrives at P3 coming from the direction of P2. Usually it will not pass through P1 or P2. These points are only there to provide directional information. The distance between P0 and P1 determines how long the curve moves into direction P2 before turning towards P3. A cubic Bezier curve and indirectly specifies the end-point tangent vector by specifying two intermediate points that are not on the curve. In this way, cubic Bezier curves are drawn. We are having some properties of Bezier curve. The basic functions are real in nature for Bezier curve. Bezier curve always passes through the first and last control points. That is, curve has same endpoints as the guiding polygon. The degree of the polynomial defining the curve segment is 1 less than the number of defining polygon points. Therefore, for 4 control points, the degree of the polynomial is 3, that is, cubic polynomial. The curve generally allows the shape of the defining polygon. Next property, the direction of the tangent vector at the end point is the same as that of the vector determined by first and last segments. Next property, the curve lies entirely within the convex hull formed by 4 control points. Next property, the convex hull property for a Bezier curve ensures that the polynomial smoothly follows the control points. Next property, the curve exhibits the variation diminishing property. This means that the curve does not oscillate about any straight line more than the defining polygon. The curve is invariant under an affine transformation. These are some properties of Bezier curve. Let's see the advantages of B-spline curves over Bezier curve. B-spline is a way to construct a curve that is interpolated between 3 or more points. It is a kind of spline generated by so-called basis functions. Bezier curves are B-splines, but the control points are different. B-splines are not used very often in 2D graphics software, but are used quite extensively in 3D modeling software. The advantages of these splines over Bezier curves are: first, the control points of a B-spline affect only their local region of the curve. Next, B-splines compute faster than Bezier curves. Third, they are smoother and easier to control. Fourth, the continuous curve of a B-spline is defined by control points. Fifth, the control points give a better idea of the shape of the curve. Sixth, they do not have the ripple, that means waves, associated with the cubic splines. Seventh, numerically more stable. And eighth, fewer bumps and wiggles. We can compare between Bezier curve and B-spline curve generation methods as: in Bezier curve generation, any shape of the curve is achieved by Bezier curve, whereas in B-spline curve generation, by using spline, we can achieve smooth curves. Second, in Bezier curve, depending on the sequence of control points, the shape of the curve gets changed. Whereas in B-spline curve generation, depending on the sequence of control points, the shape of the curve is not changing. Third, Bezier curve generation, sharp corners are achieved by passing the curve from the sample points. Whereas in B-spline curve generation, we can achieve the sharp corners by using the blending function repeatedly for the same point. Fourth difference, in Bezier curve generation, this is always passing from minimum 2 points, that is starting and ending point. Whereas in B-spline curve generation, in a special case, the curve may not pass from any of the sample points.